So, last time we were looking at solutions to Pell's equation. We showed that x square minus dy square equal to 1 has infinitely many solutions, and if you have one solution you can produce, if you have one non-trivial solution, non-trivial meaning x is not equal to plus minus 1, y equal to 0, that is the trivial solution. So, if you have any solution apart from that, you can produce infinitely many solutions by just taking integer powers of this one solution. And so, we are just trying to prove various properties of solutions. So, we were in the middle of proving the following lemma. So, let x square minus dy square equals 1 equals a square minus db square x, y, a, b are all greater than or equal to 0, then the following are equivalent, and the following statements were x plus square root of dy is bigger than a plus square root of db. The second statement was that x is bigger than a and y is bigger than b, and the third statement was x is bigger than a or y is bigger than b. All right. Okay, and maybe I said something slightly wrong the last time. It's so what is clear is that 2 implies 1. So, this is clear, and 2 implies 3 is also clear. I think I said the other way around last time. So, this was I made a mistake. So, mistake last time. I wrote this in the other direction. So, of course, if x is bigger than a and y is bigger than b, then x is bigger than a or y is bigger than b, not the other way around. And we proved something. So, we proved that. So, let us say assume so if x plus square root of dy is bigger than a plus square root of db, then x minus square root of dy is less than a minus square root of d times b, and if you add these two inequalities you get a plus x y minus b square root of d is bigger than a plus x plus b minus y square root of d, which implies that y is bigger than b, right. And if you as I said, if you subtract these two inequalities, right, okay. Okay, maybe let me not write it that way, let me. So, x a square is 1 plus db square, and I know that b is less than d already. So, what this tells me is that this thing is less than 1 plus dy square, which is x squared. So, hence a is less than x, right. So, I have proven a bunch of things, and that should okay. So, let us say right. So, let us assume, so we have proven 1 implies 2, right, because I assumed that x plus square root of dy is bigger than a plus square root of db, and I have proven that y is bigger than b and x is bigger than a. So, I have proven 1 implies 2, and so I get that 1 is equivalent to 2. Now, I should prove that and so 1 also implies 3, right. So, 1 so hence 1 is equivalent to 2, and this we know this implies 3. So, we just need to assume 3 and prove prove either 2 or 1, right, one of them. Okay. Right. So, now let us assume 3. Okay. Right. So, yeah, I mean this is kind of, we have already done this, but let me just say. So, say a is bigger, a is less than x, right. For concreteness, let us say a is less than x, and let us say a plus square root of d, b is bigger than x plus square root of dy. Okay. So, let us say that this holds. Then a plus square root of d b bigger than x plus square root of dy implies that x is a is bigger than x, right. So, that is a contradiction. So, hence this assumption must be wrong, right. So, hence this assumption. So, I am saying that assume this is true, assumption must be incorrect, right. And yeah, so hence 3 implies 1. Okay. All right. So, that is a very useful lemma that we have proven, that if you have inequality on this irrational number x plus square root of d times y, then it actually gives you an inequality on x and y. So, that is kind of an amazing thing. So, here is a theorem that we want to prove. This tells you how to find all solutions, finding all solutions of Pell's equation So, let us say assume x1 y1, x1 and y1 are both positive integers, be a solution of x square minus dy square equal to 1, such that y1 is minimal such solution, y1 is minimal among such solution, then any solution of x square minus dy square equals 1 is of the form plus minus x1 plus square root of d y1 to the power k, right. So, where k is, you are even allowed to take negative powers. And so, if you are just looking for solutions in positive integers, you just look at positive powers and plus 1 as the sign, right, plus as the sign. Okay. So, it is clear that any solution it is clear that these are solutions. So, clearly plus minus x1 plus square root of dy 1 to the k give solutions to x square minus dy square equals 1. You want to show that any solution is of this form. right. So, let us say let x 2 and y 2 bigger than 0 be such that x 2 square plus square root minus dy 2 square is equal to 1, right. Then we show that there exists k in n such that x 2 plus square root of dy 2 is equal to x 1 plus square root of dy 1 to the k. Okay, so, that is what we want to show. All right. Now, if you just look at this sequence, so consider the sequence x 1 plus square root of dy 1 to the 0, x 1 square root of dy 1 to the power 1, x 1 plus square root of dy 1 to the power 2, and so on. This is a strictly increasing sequence. This is a strictly increasing sequence, right, which means hence there exists k such that x 1 plus square root of dy 1 to the k is less than or equal to x 2 plus square root of dy 2 is less than, strictly less than x 1 plus square root of dy 1 to the k plus 1, right. It should sit between these two quantities. So, I can rearrange this, I can divide out by x 1 plus square root of dy 1 to the k and get, so hence 1 is less than or equal to x 2 plus square root of dy 2 x 1 plus square root of dy 1 to the minus k and less than x 1 plus y 1 square root of d, right. So, now you write this as x 3 plus square root of dy 3, right. You can write such an expression uniquely. So, this is x 3 and y 3 also satisfy Pell's equation, x 3 minus dy 3 x 3 x 3 squared minus dy 3 squared is also 1. Okay. And so, what we have is 1 less than or equal to x 3 plus square root of dy 3 which is less than x 1 plus square root of dy 1. Okay. So, now there are two cases to consider. Let us say that x 3 plus square root of dy 3 is equal to 1, then x 3 is equal to 1 because otherwise the left hand side is irrational and the right hand side is rational, right. And so, this gives a, so and then y 3 will be 0 and hence x 2 plus square root of dy 2 will be equal to x 1 plus square root of dy 1 to the k, right. That is what we want. So, we are done in case 1. So, if this happens, then we are done. If not, then x 3 plus square root of dy 3 is bigger than 1, right, which means x 3 plus square root of dy 3 which means by one of the lemma that we proved earlier, by a lemma proven earlier, x 3 is bigger than 0 and y 3 is bigger than 0, right. Okay, so let us summarize what we have done again. So, 1 is less than x 3 plus square root of d y 3 is less than x 1 plus square root of d y 1, and x 3, y 3, x 1, y 1 are all bigger than 0, right. So, then we have x 3 is bigger than, sorry, x 3 is less than x 1 and y 3 is less than y 1. So, that is a contradiction as y 1 was chosen to be minimal, right. So, this proves the so hence yeah, x 3 plus square root of d y 3 is equal to 1, and we are done, right. Yeah, okay. So, so this tells you that you should find a solution with y 1 minimal, right. To get a to produce all solutions, you should find a solution where y 1 is minimal. So, let us look at an example again, go back to our square root of 2 example. So, x square minus square root of 2 y square is equal to 1, right. So, what we do is we start with whatever quantities of, yeah. So, we start with y is equal to 1, and you get x square minus why do I keep writing square root of 2, I do not know, sorry, there should be 2. Yeah, so minus 2 is equal to 1, so x square is equal to 3, and this has no solution. So, you take y to be 2 and you get x square is equal to 9 and you get a solution, right. So, x is equal to 3 or minus 3, it does not matter up to sign, right. And so, 3 plus square 2 square root of 2 is a fundamental solution. Okay. All right. So, let me let us do some more examples. Just give me a second. Yeah, sorry. So, let me go back to the proof here, and I think this is not automatic. This the x 3 y 3 part is not automatic. So, this part is not automatic. So, let us yeah, we'll sort of prove this first. So the proof is complete. The proof is okay if x 3 and y 3 are both positive. So, what happens? So, what if x 3 and y 3 are not both positive? So, what do we do in that case? So, what we do is the following. So, you let alpha be x 3 plus square root of d y 3. Right. Yeah. No. Yeah. Not this. I mean, what I mean is x 2 and y 2. X 2 is bigger than 0 and y 2 is bigger than 0. It can happen that one of them is positive and another one is negative, or they are both negative. and so let me kind of do it that way. So, what if x2 and y2 are not both positive? Then we can then we can do the following. So, you consider minus 1 1 by alpha. So, this is x2 minus square root of dy2, or you consider this, which is minus x2 plus square root of dy2, right, or you can consider minus alpha, which is minus x2 minus square root of dy2. So, at least one of these, so at least one of this minus alpha, 1 by alpha, minus 1 by alpha has both positive coefficients, and then we run our argument with that and finish the proof. Yeah, sorry about that. So, that's what we do, right. Okay. Anyway, so going back to our example, so this is a fundamental unit, which means that all solutions of x square minus 2y square equals 1 are of the form plus minus 3 plus 2 square root of 2 to the power k, where k is an integer. Okay. So, this also includes plus 1 and minus 1, by the way, because you can take k to be 0. Alright. So, another example is you look at x square minus 3y square equal to 1, and in this case, of course, you can try y to be 0, you get, so y equal to 0 is, you always get the trivial solution. So, you try y equal to 1, you get x square equal to 4, and so x is equal to 2, and you get 2 plus square root of 3, and so these are all the solutions. Right. Let us try something maybe bigger. So, x square minus 5y square equal to 1, and so you try y equal to 1, you get x square is equal to 6. So, there are no solutions. You try y equal to 2, and you get x square is equal to 16, 21. There is no solution. You try y equal to 3, so you get x square equal to 46. So, there are no solutions. Y equal to 4. So, 16 into 5 is 80, and you get x square equal to 81. So, you get x is equal to 9. So, you get 9 plus square root of 5, 4 square root of 5, right. So, so all the solutions are of the form 9 plus 4 square root of 5 to the k. Alright. So, this gives you all possible solutions of this, this particular Pell's equation. Now, of course, you can ask a question, how far do I have to go checking? So, how far do we need to go before we get a solution, right. So, that is a very valid question, because all that we know is there is a solution. We do not know how far we need to go, I mean how many values of y do we need to take before we get a solution, and so there should be some way of getting a bound on y before we start getting a solution, and there are some good bounds on y. How far we need to go, but we are not going to go into that. So, you do not have to go more than d for example, but we are not going to prove that. So yeah, so in practice you will get a solution pretty quickly before by not trying too many values of you do not have to try too many values of y. So, for example, here you don't really have to try this. So, don't need to try this. And why is that? Because you see 5 is 1 mod 4 and y square, if it is odd, will also be 1 mod 4, and when you add that to 1 you will get something that is 2 mod 4, and so you know that this will never give you a square. So, a number a square is never 2 mod 4. So, you only need to try with even values of y. So, you can do all these sort of analysis, but even without doing, you do not have to go too far to find a solution. Okay, so next time we will start the study of biquadratic fields. Yeah, that is it. Thank you.